All right, we just got done with the problem in which we were looking at the spontaneity reaction at 25 degrees Celsius. Now we're going to look at the same reaction, but we'll just change the temperature over. So we'll take a look at running that a second time. Delta G is still equal to negative 92 kilojoules. But this time with the temperature at 500, we'll be at minus 773 Kelvin. I don't know why I wrote this time and not last. And again, don't forget that the delta S value has to be in the same units as the delta H value. So typically we switch over to kilo, but you could do either one. And I'll go ahead and put that in there. And this time the value comes to 61 kilojoules, which of course is positive. And if we're looking at delta G, the fact that this comes out to a positive value tells us that it is non-spontaneous. And again, this is at 500 degrees Celsius. So interesting, seeing how the temperature will change the spontaneity of a reaction. At 500 degrees Celsius, it is non-spontaneous. All right, interesting. So we can kind of take a look and just come with a final statement on this one as far as what's going on with this reaction. Well, this reaction works best at low temps. All right, there we have it. Let's take a look at another one. So keep on pushing through the notes. Delta G F, and we'll figure this out here in a second. We're looking at standard states. If something is in its standard states, just like delta H, the value for delta G is going to be 0. So how spontaneous is it making hydrogen from hydrogen? Well, it's not, it just is. So the delta F is referring to the spontaneity to make something from itself. So those values are always going to be 0. So if we look in the back of the book and you have an element, say hydrogen, you can see that it has a value for delta S, but it doesn't. It's a 0 value for delta H and delta G. So again, no energy is needed. And this is specifically for elements. You don't make elements from themselves in their standard states. So when they say standard state, we're talking about 25 degrees Celsius. Those are the conditions we're looking at. All right. Through a derived formula, add a phase change. Which of course is reversible, right? That means delta G is going to be 0. We're at equilibrium, phase change. And if we're looking at the delta H minus T, and we'll put B in here for the temperature of boiling, just as an example. We can use this formula as kind of like an estimate to figure out what temperature that would be. It's close, it's not perfect. We say can use this to estimate. I'm going to underline that because I can't italicize it. Estimate the temperature. It's not perfect, but it's close. At a phase change. All right, I'm going to change over another sheet here because this one's getting full. Slide this down. Okay. And again, based on that equation I said there a second ago, we can say the temperature, in this case boiling, would be equal to delta H. And again, this is not on your equation sheet, so you would have to understand how this would go together. The delta S there. And if we just want to look at it as an example, we can look up carbon tetrachloride liquid, and we were talking about boiling, so we'll stick with that. Gas. And we have some values that we can look up. Let's see, the delta H for this carbon tetrachloride is 32.6 kilojoules. And the delta S value, standard, is positive 95 joules per Kelvin. And if we lump this into the formula we have over there on the side, you would get 0.6 kilojoules over 0.095 kilojoules, keeping the units the same, is equal to 343 kelvins, or if you want to call it Celsius, right around 70 degrees Celsius. So we can actually use that equation we were looking at before at a phase change to figure out what temperature that would be by using their standard values at 25 degrees Celsius. All right, next problem. If we look at a whole different set of circumstances, we were looking at a couple with the changes in temperature, or looking at a phase change. In this set of circumstances, we're going to look at what happens if we are not at standard conditions. So this will be a whole different setup. Free energy. And guess who's back? Equilibrium. Now, we mentioned before that if you are, whoops, how about I do that? At equilibrium, delta G is going to be equal to 0, okay? And we have another delta G that we mentioned before. If we have this little naught guy, then we are considered at standard conditions. So delta G naught is under standard conditions. And that happens to be 1 atm. We haven't mentioned this one yet. 1 molarity. And again, you're also at 25 degrees Celsius. And just a couple of things to mention. We have pure solids and liquids. And typically you're just referring to water. Other things are going to possibly be aqueous. So we'll see how this works out. Okay, moving forward. Most reactions are actually non-standard. Excuse me. We can use a new equation to see how delta G varies with these changes from non-standard. And that equation is delta G under non-standard conditions. This is where it gets a little wonky. Delta G standard. So how does it change? I'm just looking at spontaneity. This is what we're referring to. It just happens to have that same symbol. So what is the spontaneity of the reaction compared to normal standard conditions? plus R, and we'll get to that in a second, at temperature in kelvins. And we're going to go natural log of Q, these non-standard conditions. So we've talked about this before when we did equilibrium, Q versus K. These are non-standard conditions. Okay. If Q is standard, think about the math, then the conditions, or it is standard conditions, then, excuse me, it's equal to 1, and then the natural log of Q is equal to 0, and then delta G is simply going to equal those standard conditions. So if everything's in its standard state, easy enough. Okay, let's use that same equation we've been using. You have nitrogen plus hydrogen producing ammonia. And we'll give it some non-standard conditions. We'll say nitrogen happens to be 1 atm. We'll say hydrogen happens to be, I'll say at 3 atms. And then we'll say ammonia is at 0.5 atms. Okay. So given this information, we can very quickly do like a Q based on the equation that we have. So again, equilibrium stuff, we're pretty familiar with that. Q is going to be equal to products of reactants. Don't forget each one is raised up to its value based on the concentrations that I have for these guys. Ammonia is 0.5. Its coefficient value is 3, or excuse me, where's that one at? Should be 3. Looking at my sheet, it looks different. I'm sorry, I put the wrong number here. Sorry, this should be a 2. So there we go. I was like, why does that not match? Should be 2. And 1 for nitrogen is simply 1. And 3 for hydrogen is raised up to the third. That gives me a value of 3.3 times 10 to negative 3. Okay. And again, if I look in the back of the book, I can see the delta G naught is equal to negative 33 kilojoules. And I believe we did that on a problem just previously. Kilojoules per mole from the back of the book. All right, now if we plug this in and actually get a equation for this, see if I can rip through this pretty quickly because I'm running out of time for this video. We get negative 33 kilojoules per mole. And again, just following through on that equation just above. 8.314. Notice the R value we're using. Because we're talking about energy, we're going to use this one. But also notice that I changed it from joules to kilojoules to make sure all the units are going to jive out here. Per mole per Kelvin times the temperature in kelvins, 298. This happens to be run at 298. And then using the natural log of our 9.3 times 10 to negative third. Okay, and that will equal out to be negative 44.9 kilojoules per mole, which is negative. So it is more spontaneous based on the pressure conditions given. All right, this will be the end of the lecture for number 5. Good.